In this video, we're going to introduce approximate solutions and the least squares problem for cases when the system of linear equations does not have an exact solution. So we're going to review the need for approximate solutions, introduce norms as a way of measuring the size of an error, define the properties of norms, and then conclude with the least squares problem. We've seen already that systems of linear equations of the form matrix A times a vector W, which is unknown, equals a known vector D, play an important role in classification problems as well as modeling data. We also looked at the conditions under which this system of linear equations has an exact solution for W. And the only time we get an exact solution is when the vector D lies in the subspace spanned by the columns of A. Because here we see that this system of equations expresses D as a weighted combination as the columns of A. Now this condition is rarely satisfied in real machine learning problems due to noise, limitations of the model, other non-ideal effects, and so on. So the question that we ask, and it's a very important one that we'll spend a lot of time on, is can we find a solution W so that AW is close to D in some sense? So in order to explore this idea, we're going to define the error E as the difference between AW and D, and then obviously we want this error vector to be small. So if we talk about a vector being small, we have to somehow define what we mean by the size of that vector. And a vector norm precisely does that for us. Now there are many different vector norms, and we're going to look at a couple here. For example, the one norm of a vector E is the sum of the absolute values. And this is sometimes called the taxicab norm or the Manhattan norm because it corresponds to the distance that you would travel if you were taking a taxi on a rectangular grid of streets. If you want to go from the origin to point E, you have to take a street that first goes west and then a street that goes north. Now the L2 norm is the sum of the squares of all the elements in the vector square root. So this is the direct distance from the origin to the point E in space. And this is also known as the Euclidean norm. It's probably the one that's most familiar to most of you. We can also define an L infinity norm, which is given by the max over all the elements of the absolute value of each component. If we look at some point here, which is E, then the max coordinate is going to be along the horizontal axis, and that'll be the L infinity norm, sometimes also called the sup or the max norm. Now in general, this leads us to the idea of LQ norms, where we define the LQ norm of a vector E as the sum of the magnitude of E sub I raised to the qth power, and that whole quantity raised to the 1 over q power. And each of these falls into that pattern for specific cases of q. Here we have q equals 1, here we have q equals 2, and so on. Now it's useful to think about norms geometrically in addition to how they measure distance in the coordinate space. It's useful to think about what's called the unit ball. And this is the set of all vectors, say x, which have unit norm. The 2 norm is just the set of all vectors x where the sum of the squares is 1. That describes a circle. All the vectors on this circle have unit norm. Now in the L1 case, all the vectors that have unit norm lie on a diamond. Because remember, in this case, we're going to add the absolute value of the horizontal coordinate to the absolute value of the vertical coordinate. Setting that equal to a constant gives us a line with slope -1 in the first quadrant, +1 in the second quadrant, and so on. And then the L infinity ball is a square, because here we're looking at the set of all vectors with max element being equal to 1. And on this leg, that corresponds to the horizontal component being 1 and the vertical component being less than 1. Then when I get on this leg, this is the vertical component being 1 and the horizontal component being less than or equal to 1. So the geometry of these balls helps us later understand the solutions to certain problems and why they behave in the way that they do. Now formally, we define a vector norm as an operator that maps from n-dimensional space to a scalar, and it satisfies the following properties. First of all, the norm of any vector x has to be greater than or equal to 0. Secondly, norm of a vector x is 0 if and only if that vector is the all zeros vector. So the only point that has 0 norm is the origin. If I scale a vector by constant b, that scales the norm by the same constant. And that applies to any real b, to apply to any vector in x. What this means is here's x, say in orange, and then if I scale x by b, I make it longer in this example, I've drawn that in blue, then the norm of the scaled vector has to be b times the norm of the original unscaled vector. And the fourth property is that the norm must satisfy the triangle inequality. In other words, the norm of the sum of two vectors has to be less than or equal to the sum of the norms. A little picture illustrates why this is called the triangle inequality. If I have a vector x pointing in this direction, I have some other vector y, and I add those two, then that forms a triangle. The length of the side representing the sum of these two vectors has to be less than the sum of the lengths of the individual vectors. So let's take an example and look at the L1 norm, which we defined in the previous slide as the sum over all the elements of the vector of their absolute values. Well, since this is a sum of absolute values, clearly it's always going to be greater than or equal to 0. Now what happens when x is equal to 0? Well, then you're summing the absolute value of 0, which is 0. So the only if part of this holds. If, on the other hand, the L1 norm is 0, that's telling us the sum of absolute values has to be 0. And since absolute values cannot be negative, the only way for this to be true is if each absolute value must be equal to 0, and that implies, of course, that x has to be equal to the all zeros vector. Now the third property is that if we scale x by b, the norm should scale by b. And that's easy to show by applying this in the formula, where we'll pull the b out from the norm of b times each element, and that would give us b times the absolute value of x by. We can pull the b out of the sum and arrive at this line here. And clearly this is b times the 1 norm of x. And finally, the triangle inequality also applies, because if I take the 1 norm of x plus y, that's just the sum of the absolute value of x plus yi. Since these are real numbers, the absolute value of a sum of two real numbers is less than or equal to the sum of the absolute values. There's equality when both numbers are positive or negative, and there's inequality when one of the numbers is negative and the other is positive. So I can rewrite this as being bounded by the sum of the absolute value of xi plus the absolute value of yi, and this is just the 1 norm of x plus the 1 norm of y. So we've shown that the triangle inequality also applies. So one property of norms that applies to LP norms, like we defined in the previous slide, is the inclusion property. So we're going to define constants p and q that are bounded where p is less than or equal to q, and both of these constants are greater than 1. In this case, the LQ norm is less than or equal to the LP norm. So q is bigger, but the LQ norm ends up being guaranteed to be smaller. As an illustration, looking at the max of the absolute value of any element of the vector has to be less than the sum of the absolute values. So here we've just shown that the infinity norm is less than the 1 norm, which is the two extreme points of this inclusion property. Now the reason we have these different norms is because they allow us to pursue solutions that have different attributes. For example, the 1 norm is often used in machine learning to find solutions that have a sparse character. In other words, a fairly small number of the entries are non-zero. On the other hand, the L infinity norm allows us to look for solutions that have constant magnitude. And finally, the L2 norm is used to minimize the squared error. So we began by considering the system of linear equations. If we couldn't get an exact solution, could we have a small solution? And that's where we're going to want to include the L2 norm. We're going to try to find a solution W that minimizes the squared difference between AW and D. And this is called the least squares problem. So if you can think about what's happening geometrically, we know that our solution AW has to lie in the span of the columns of A. So in 3 dimensions, if A is rank 2, then the span of A defines a plane like I've illustrated here by the green rectangle. So AW has to lie in that plane. Now D, in general, if there's no exact solution, doesn't lie in that plane because it doesn't lie in the subspace spanned by the columns of A. And therefore, there's some difference in error vector E between D and AW. In the least squares problem, what we're trying to do is make this error vector to have the smallest Euclidean norm. In other words, that the sum of the squared errors is minimized. Now we'll look at how to find that solution in subsequent videos.